on the topic of convergence, right, sometimes we can find the limit easily. Sometimes it might not be so easy. And other times we are really just interested in whether it converges or diverges, but we don't really care about the limit if it is convergent. We just want to show, yep, it's going to reach a value at some point. We don't care what it is. And so we want to be able to conclude convergence, but not necessarily find the limit. We have more tools. The first thing we need to talk about is what a monotonic sequence is. It's kind of a catch-all to talk about whether a function is increasing or decreasing. You can see that at the bottom of the screen. So increasing or decreasing, we just call it monotonic. And we would say a sequence is strictly increasing if, I know you have to look through the notation just a little bit here, but it says if an minus 1 is less than an. So as we progress in the sequence, as we keep going, the values continue to get larger. Okay, and strictly decreasing would be if we are progressing in the sequence, the values get smaller in value. And then along with this, we can talk about weakly instead of strictly. Weakly would just be less than or equal to, if it was weakly increasing, and weakly increasing, weakly decreasing would be less than or equal to as well. But just to familiarize yourself with the language. Okay, so we want to figure out whether these sequences are monotonic or not. Okay, so here are some examples. Are they monotonic? Well, the biggest thing you can do is maybe from the get-go, it's not apparent, so let's just try substituting a value. So maybe like make an n and an chart. So if n is 1, what do we get? We get 1/5. If n is 2, all right, we get 1/7. As n is equal to 3, we get 1/9. Okay, you get the idea. Okay, go on. So this one looks like it is decreasing, so we would say yes. Okay, it is monotonic. But now that really isn't enough to a mathematician. You might need to review induction, right? So induction, very, very useful. Okay, I'll give you an example. So when you're doing induction, you should define a statement Pn. We want to say that an minus 1 is bigger than an. That's the idea for decreasing, right? So we want to show, for induction, we want to show our base case. N is equal to 1. Okay, and we have maybe n is equal to 2 rather. Okay, doesn't matter, you just need to show an example. And so we have that a1 is bigger than a2, and we have 1/5 is greater than 1/7. That's a check. Okay, so now I didn't leave myself enough room vertically, so I have to work horizontally. So then next I need to state is my induction hypothesis. I assume PK is PK is true. Okay, and I'm just going to write out PK for my own sake. This is going to be AK minus 1 is bigger than AK. Okay, so that's my induction hypothesis, and now I do my induction step. And I say, show P of k plus 1 true. Okay, so to show this, I need to start from something that I know. I know that PK is true, so I know that AK minus 1 is bigger than AK. Okay, and again, this would be that 1 over 2 and then k minus 1 plus 3 is bigger than 1 over 2k plus 3. Okay, and now in this step, this is a little tricky to maybe figure out, but here's what I'm noticing is that if I make the denominator larger, the overall fraction gets smaller. So I can say this is bigger than 1 over 2k plus 5, which is equal to 1 over 2 parentheses 2k plus 1 plus 3, and then that, my friends, is indeed ak plus 1. So this is saying that ak is bigger than ak plus 1, which is statement pk plus 1. So then I would come up here and say, since pk plus 1 is true, Pn holds for all values, or all natural numbers n by the principle of mathematical induction. Okay, so again, just to recap, make sure to start off with your overall statement, identify a base case. I did n is equal to 2. Really, any example will work. Show your induction hypothesis, do your induction step, and then make sure to conclude. Okay, that's how formal induction is done. Now, our next example, again, you might want to make a little table just to kind of think through the process of convergence and divergence for yourself. And so here I get 1 plus 1 over 1 is 2, right? And then 2 plus that is 2.5 if you like mixed numbers, okay? 3, and then so this is 3 1/3, and then 4 would be 4 1/4, okay? So this appears to be increasing. So this we would say is monotonically increasing. And induction will work to show this, but you can maybe also just show it directly. The idea is you want to show that n plus 1 over n is less than n plus 1 plus 1 over n plus 1. And if you follow that math through, right, the n's would drop off, and you'd have 1 over n is less than 1 plus 1 over n plus 1. Okay, subtract these, the n minus, or n 1 over n plus 1 over, so we'd have 1 over n minus 1 over n plus 1 less than 1. Okay, and then you have to, for time purposes, I'm not going to go through it, but you would arrive at you have to do a little bit more work, and then ultimately this is all less than 1, which is a true statement. Okay, so it does end up working. You just need to go through that. Okay, so we talked about monotonic. The other thing that we will need to show eventually is that sequence is bounded, and so bounded is really nothing different than what we might expect. Typically we use it to indicate that it's bounded both above and below. So bounded above just means that we can find a value that the sequence lies below it for all values in the sequence, and then bounded above and then bounded below is that it would be bigger than another value. So just as a diagram here, with the an is our tangent sequence. So if I look at n and an, pi over 2 ends up being right smack dab in the middle, and then if we look at pi and 0, the sequence as a whole, the sequence of values, I'm not giving you a defined axis here, but we end up getting something like this, and we end up being bounded above by pi and bounded below by 0. I actually can't have values over there. Oops, undo. Oh, okay, we'll just leave that. But so this would be an example of a bounded sequence. It's bounded above by pi, bounded below by 0. And so in the next video we'll put these definitions into very good use.